Hello, in this lecture we will discuss fluid flow measurement. So here we will be talking about the apparatuses used in measuring fluid flow and as well as what are the computations used in determining the fluid flow. So let's start. So what are device coefficients? So device coefficients having a symbol of C or CD is the ratio of the actual discharge through the device to the ideal theoretical discharge which would occur without losses. So this device coefficients is the coefficient because used because uh, the theoretical discharge, which is based on the velocity and the cross-sectional area of the pipe, is not equal to the actual flow of the fluid that is traveling on that particular conduit. So theoretically, we can determine the flow rate using the area and the velocity by this formula, area times velocity. But in reality, the value of that flow rate is not the same to the actual discharge. So we have device coefficients that will be used in determining the actual discharge. So the device coefficients can be computed as the ratio of the actual discharge divided by the theoretical discharge. So if we have a predetermined coefficient of discharge C or CD, and we have a theoretical discharge QT, we can determine the actual discharge using this coefficient. So it means that we have to multiply the coefficient of discharge to the theoretical flow rate to determine the actual discharge, okay, or flow rate. So that is pertaining to the discharge, actual and the theoretical discharge. So that's the coefficient of discharge. How about coefficient of velocity? So this is also the ratio of the actual mean velocity to the ideal theoretical velocity. So same solution is the ratio of actual velocity to the theoretical velocity. So this is our coefficient for velocity. Okay, to determine the actual velocity having a theoretical velocity, we can use this coefficient. Also, we have the coefficient of contraction, CC. It is the ratio of the actual area of the contracted section of the stream or jet to the area of the opening which the fluid flows. So again, same concept. It is just the ratio of the theoretical actual rather to the theoretical opening. Okay, so it means that here in coefficient of contraction, it means that the real area of the water that is traveling in this on this conduit is not the same as with the theoretical area or the actual opening of the pipe or conduit. So it is due to some friction or other losses that would cause the fluid to have a cross-sectional area, and that is not equal to the opening of the pipe. So these are the coefficients that we can use in determining the actual flow rate, actual area of the stream or jet, and the actual velocity. So the relationship between those coefficients is the actual discharge Q is equals to the product of C or the coefficient of discharge to the theoretical discharge. Also, we have a relationship between the coefficient of discharge, coefficient of contraction, and coefficient of velocity. So this coefficient of discharge is just equals to the product of the coefficient of contraction and coefficient of velocity. Okay, next. So the first device that we will discuss here in measuring fluid flow is the orifice. So an orifice is an opening, usually circular with a closed perimeter through which the fluid flows. It is used primarily to measure or to control the fluid flow. So this is an example of an orifice. So where we put orifice plates in between the pipe to measure the flow rate on this pipe. Okay, so what are the formulas that we are going to use in measuring the velocity discharge in the pipe? So here are the formulas. So these are just based on rectilinear motion solutions. So for the theoretical velocity, okay, so let's say we have here okay, body of water with a given height h, okay, and our opening is at the bottom or right here. So say this is our initial velocity. The fluid is moving from the top going to the opening of this container. So initially we have an initial velocity and we have a final velocity of v1. So from solutions in rectilinear motions, we have final velocity squared minus initial velocity squared equals to 2gs. So the s is h, or the vertical distance. So our initial velocity is 0, so that will be cancelled out. So we have v1 squared equals to 2gh. Therefore, the velocity at the opening at the bottom is equals to the square root of 2gh. So this is where that formula came from. Okay, so the theoretical velocity is v1 equals to the square root of 2gh. So h is the head of the liquid from the opening. Okay, from the opening of that container. So orifice can be placed at the bottom, on the side, okay, on the side. So in which if we are going to measure the head, it should be measured from that opening going upwards. Okay, for the actual velocity, just multiply the coefficient of velocity to this theoretical velocity. On the other hand, we have theoretical discharge. So we know that Q discharge is equals to AV. So if this is the theoretical, therefore the actual is just it will be multiplied by coefficient of discharge. Okay, coefficient of discharge AV. So for the theoretical discharge, we have area times V. So this V is the square root of 2GH. So therefore, we have this formula A, the square root of 2GH. So for the actual, just multiply CD, where V is equals to the square root of 2GH. Then we have this formula right here for the actual discharge. So you can put CD or only C for coefficient of discharge. So CD A, the square root of 2GH. So for H, it is just the total head producing flow in meters or feet of the flowing fluid. So it can be noted that H is the sum of the fluid energy upstream less than the flow energy downstream. Or simply take the difference of the head on the upstream and the head on the downstream. So that H that will be computed can be used in determining the flow here at this orifice. So here are the values of H in various conditions. The first one is we have a container, open container with height H measured from the orifice, okay, to the liquid level. So that H, the capital H, which is the head required in determining the flow on the orifice, is just equals to the head from the opening to the liquid level. So the next one is if that container is accelerating upward. So here is the equivalent value of our h. So that h is equals to head multiplied by 1 plus the acceleration divided by acceleration due to gravity. Then if we have a closed container where there is an additional pressure of air above the liquid, so the total head is just equals to the height of the liquid measured from the opening to the liquid surface added by the pressure head due to the air pressure. Then if we have multiple layers of liquid within that container and an additional air pressure, so we just take the sum of the pressure heads from the opening of the orifice. So head, the H2 measured from the opening to the liquid surface, then H1, the height of the liquid layer, then added by the pressure head due to this gas right here. So make sure that you have to convert that the head of these fluids to the head of the liquid that is on the opening of this container. So if this is our fluid here, which has a unit weight of gamma 2, so we have to express the head of this layer above gamma 2 into this type of liquid. So here's our conversion factor, which is just the ratio of its unit weight. So gamma 1 divided by gamma 2. So to convert this head, which is equivalent to the head of this liquid. So then add another head. So P over gamma. So this gamma for this pressure of this air right here. So we will divide that by the unit weight of this liquid at the opening. Okay, so take note if we have multiple layers of fluids in a container, so make sure that you have to convert these heads into the equivalent pressure head of the liquid that is in the opening of or on the orifice. Okay, so that's why we convert this layer of pressure head multiply gamma 1 and over gamma 2, and for this pressure of gas here, it is divided by the unit weight of this liquid, again gamma 2. Okay, so for submerged orifice, so just take the difference in elevation measured from the opening of the orifice, the upstream and the downstream. So the difference in elevation, h, that will be your h that will be used in measuring the velocity and discharge. Okay, so let's solve now some problem. Example number 1, we calculate the discharge in liters per second through a 100 mm diameter orifice. So our diameter for the orifice is 100 mm under a head of 5.5 meters of water. Assume coefficient of contraction 0.61 and coefficient of velocity is 0.98. So again, the coefficient, the discharge, actual discharge is equals to coefficient of discharge multiplied by the area and the square root of 2gh, or this is the theoretical velocity. Okay, so the relationship between the coefficient of discharge is equals to the product of coefficient of contraction and coefficient of velocity. So it means that the product of 0.61 and 0.98, that's the value for coefficient of discharge. Okay, 0.61 times 0.98, 0.5978. Then we compute the area. Okay, or we can directly use this formula, this one. So that's Q equals to CD A the square root of 2GH. So CD is 0.5978. Area is, we have diameter, so pi d squared over 4. Convert that to meters. So 0.1 meter is to 2 divided by 4 pi d squared over 4 multiplied by the square root of 2GH. So 2 times 9.81 meter per second squared times the h of 5.5 meters. So the Q is equals to, okay, 0.04877. 77, that's in cubic meters per second. So let's convert that to liters per second. Just multiply 1000. So multiply 1000, that will be in liters per second. That's 48.77 liters per second. So that's the answer for example number 1. Okay. Next, example number 2. Let's determine the discharge through the 140 mm diameter orifice, which is right here, where we have a coefficient of discharge of 0.62. So here this is two chambers, so both have air pressure 50 kilopascal and 15 kilopascal. So in solving the actual discharge, we have C A the square root of 2G H. So what is H? H is just the difference of the head on the upstream and the head on the downstream. Okay, so for the head on the upstream, so if this is the opening of the orifice, so we have a head of 3 meters added by the air pressure. Okay, so we have to convert the given pressure 50 kilopascal to its equivalent pressure head. So of course we will use the unit weight of this liquid, which is water. So we have 50 kilopascal divided by the unit weight of water, kilonewtons per cubic meters. Then it is subtracted by the head on the downstream. So since the water here on the chamber B is that it is below the opening of the liquid, so there's no additional head here. Okay, but if it is above the orifice, so we have a head that will be subtracted on the head of the upstream. So there's no H here head for the water, but we have a given pressure, air pressure inside this container, chamber B, which is 15 kilopascal. So it means that that head will be, that pressure will be subtracted on the head on the upstream. So again, we will convert this air pressure to its equivalent pressure head. So P over gamma. Okay, 15 kilopascal divided by 9.81 kilonewtons per cubic meters. So the head is equals to 3 plus 50 over 9.81 minus 15. Okay, so that's 6.5678. Okay, 79. 568 meters. Okay. Then we can now compute the discharge. Q equals to C 0.62, the area, okay, pi d squared, 0.14 meter is 2 over 4, then square root of 2gh. So 2 times 9.81 multiplied by the head, 6.568. Okay, so Q is equals to okay, that's 0.108 cubic meters per second. So that's the discharge on the orifice. Okay, that's the actual discharge. Okay, so yeah. Next, an open cylindrical tank, 2.4 meter in diameter, yes, and 6 meters tall, has 1 meter glycerine, 2.5 meter water, and 1.5 meter oil. So given are their specific gravities, equivalent specific gravities, we have to determine the discharge through the 125 mm diameter located at the bottom of the tank. So what will be the discharge here? Assume the coefficient of discharge is 0.65. So again, discharge, if we have a given coefficient, so it means that the required discharge there is the actual discharge. So we have to multiply C to the area and the velocity. Velocity is 2gh. Okay. So to compute h, again, since this is a container which contains several layers of liquid, so since at the opening we have a liquid that is glycerin, we have to convert the equivalent head for water and oil into glycerin. Okay, so means that to determine the total head H, what we need are the head for the glycerin, head for the water, and head of oil. So again, we will convert the head of water and head of oil into glycerin. Okay, so that the head should be consistent onto what type of liquid that we're using. So head of glycerin, automatic, we copy that 1 meter. But for the head of water, we have 2.5. So the conversion factor is just equals to the ratio of the head of the unit weight or the specific gravity of water, because we can use either the ratio in converting the head of a particular liquid into another liquid. We can use the ratio of its unit weight, okay, glycerin, or we can also use the mass density, and we can use as well the specific gravity of these liquids. Okay, so since the given data here are specific gravity, we will use specific gravity. So the ratio of the unit weight of, or the specific gravity of water, which is 1, divided by the specific gravity of glycerin, which is 1.5. Then for the head of oil, 1.5 meters will be converted. So multiplied by the ratio of the specific gravity of the oil divided by specific gravity of the glycerin. So that's your total head. Okay, that's 1 plus 2.5 multiplied by 1 over 1.5 plus 1.5. Okay, so the total head is 3.487 meters. 3.487 meters. Now we can substitute it on the formula. Q equals to C 0.65, area 125 mm diameter, so pi 0.125 meters, 4 divided by 4 multiplied by the square root of 2 times 9.81, and the H 3.487. Okay, so the Q is 0.65 times 0.066. Okay, so in the discharge, okay, 0.066 in cubic meters per second. So that's the answer for this example. Okay, next problem. Last example, we have a large cylindrical steel tank 4 meters high. Okay, 4 meters. And with its bottom on a level ground contains 2 layers of liquid. The bottom layer is 2 meters water, and the top layer is occupied by a liquid whose specific gravity is unknown, which has a depth of 1 meter. A 50 mm diameter orifice, okay, is 1 meter. The opening is 1 meter below the interface between the two liquids. Then we have a given coefficient of velocity of 0.98. The jet from the orifice hits the ground at 2.75 meters horizontally away from the vena contracta, or the opening of the orifice. Determine the specific gravity of the liquid at the layer. So what will be this specific gravity right here? So based on the given, we have a distance 2.75 meters, and we also have it is measured 1 meter from the bottom of the tank. So water is flowing from the orifice and it reaches that point, which is 2.75 meters. So here on this example, we will use the principles of projectile motion. So because the water is flowing from this opening, so it means that its initial velocity is pointing to the right. Okay, pointing to the right. So it means that that initial velocity right there is also your actual velocity that can be used using this formula, cv the square root of 2gh. So but yet we can't determine that yet because we have several unknown values. So our goal is to determine this velocity right here. So as we know, in projectile motion, so along its motion, its velocity along the horizontal is always the same. Unlike the velocity along the vertical, it is varying due to the effect of gravity. So we will focus on the uh, horizontal velocity, which is also your initial velocity and the actual velocity. So it says there that it reaches this point right here. So as we recall, we have several formula that we can use in in projectile motion in order for us to determine this velocity. So we have a given distance s 2.75, so we can use that. So the distance for along the horizontal is just the product of the velocity along x, initial velocity along x, multiplied by the time. Of course, we don't have value for the time here, so we need other formulas. We can use, so to determine this time, we will use now the velocity along the vertical, okay, v o y. Of course, that value for the velocity along the vertical, it is varying, it increases, okay, from the opening of the orifice up to this point. So initially, since the direction of the orifice is along the horizontal, so the initial velocity along y is 0. So from that, since we have other givens such as this vertical distance 1 meter, which is measured from this ground surface to the opening of of the the orifice, so we can use that. So that is y. So as we recall the formula, we have y for vertical distance for projectile motion. We have v or yt plus 1 half gt squared. Okay, so since our initial velocity along y is 0, okay, and we have a y value of 1 meter, where we have 1 half g, so it is going downward, that's positive 9.81 meter per second squared, and we have time raised to 2. So 1 meter divided by 1 half, 9.81 meter per second squared, is equals to t squared. So take the square root of both sides to determine the time. So t is equals to, okay, square root of 1 over 1 half times 9.81. That's 0.4515 seconds. So from that, we can now determine this initial velocity x using this solution right here. So means v initial along x, or that is also your initial or the actual velocity, that is equals to s over t. So that s, we have a given horizontal distance of 2.75 divided by the time 0.4515. So that's the time in which the water from the orifice, opening of the orifice, reaches this point. So it is the same time, that horizontal distance is just the same time that is used with using the vertical equivalent of the velocity. Okay, so going back here, v o x is equals to 2.75 over 0.4515. So that's 6.091 meter per second. Okay, so this v initial x along x is your actual velocity, since our opening is on the right side of the container. So it means that the direction of the fluid will be tangent on this surface. It is along the horizontal. So using this formula for the actual velocity, we have CV A. Okay, forget. Sorry, no A because that's for discharge. CV square root of 2gh. Okay, that's it. From here, we can determine this value for h. Okay, the value for h. So let's determine h by dividing both sides by CV. The square root of 2gh. Then take the square. We have VA over CV squared equals to 2gh. And divide both sides by 2g to determine h. Okay, so let's substitute now the given. So the given are the actual velocity, this one, 6.091 meter per second divided by CV. CV 0.98 squared, okay, divided by 2g. 2 times 9.81 meter per second squared. That's your h. So solve that. 6.091 a squared 0.88 squared 2 times 9.81. Okay, the answer is 1.969 meters. So this is not yet the answer. This is just the total head. Okay, this is the total head. But since we have different types of liquid, okay, it means that the head of this particular liquid, when we compute this H, is converted into water. So it means that the head of water added by the head of that particular liquid is converted into the head of water by multiplying either the specific gravity, the ratio of their specific gravity, or their unit weight. So since here what is required is the specific gravity, so we use specific gravity. So the specific gravity of the liquid divided by the specific gravity of water. Okay, and then substitute now the values. 1.969 equals to head of water. So from the opening up to the water surface is 1 meter. Okay, just copy that. And for the head of that liquid, that is 1 meter, we convert that to the specific gravity of the liquid divided by the specific gravity of water, which is 1. Okay, so it's just 1. So 1.969 minus 1 is equals to the specific gravity of that liquid. So the answer is 0.969 meters. That's the specific, we don't have a unit for specific gravity. Okay, so this is 0.969. Okay, as liquid. Because we multiplied it by 1 meter. Okay, we don't have a unit. That will be cancelled out. Okay, so we don't have it. That's unitless. 0.969 is your specific gravity. Okay, so that's the answer. Okay, that ends the first part of this lecture.